Hello, welcome to my video series of algorithms. In this video, I would like to discuss the basis of algorithms. First, let's take a look at the major components of an algorithm. An algorithm should contain three parts: the input, the output, and the procedure. You can think of an algorithm as a function or subroutine in a programming language, where we need to specify the input parameters, the return type, and the function body. These components correspond to the input, output, and the procedure in algorithms. You can also think of an algorithm as a black box that takes in some inputs and produces some outputs. The input of an algorithm corresponds to the information required to execute the procedures. For example, an algorithm that calculates the area of a circle needs information regarding the diameter of the circle. And a sorting algorithm requires a set of numbers to sort. In some cases, the input could be an empty set, which corresponds to functions or subroutines that do not need any parameters. Know that it is very important to precisely specify all assumptions or expectations we have made to the input. This is because in many cases, if the assumptions or expectations are not met, the algorithm cannot properly solve the problem. For example, imagine an algorithm that tries to find the minimum number among a set of numbers by selecting the first number. For this algorithm to work, its input must be a list of numbers sorted in ascending order. Some other examples of big impacts on the algorithm made by nuances of the inputs include whether cycles are present in graph, whether negative edges are present in the graph, or whether the input tree is a binary tree, etc. Now, let's look at the second component of algorithms, the output. As the name suggests, an output is the result returned by an algorithm. For example, for a sorting algorithm, we'd expect that it returns a list of sorted numbers. For an algorithm that finds the shortest path, we'd expect that it returns a path, and so on. Unlike input, which is optional, all algorithms must have some outputs. An output could be as simple as yes or no, but it cannot be empty. This is because without an output, we don't even know whether the algorithm is executed. Not to mention that algorithms without output have no practical value at all. Know that although in programming languages, functions or subroutines can be defined without any return type, these functions or subroutines still implicitly output something, such as modifying some variables in your program. For example, a print function usually does not have any return type, but it prints some information to the screen. The information printed is considered as a kind of output. Similar to input, it is also very important to specify the format and properties of the output precisely. This is because the output of some algorithms may serve as an input for other algorithms. For example, consider two algorithms, where one sorts a set of numbers in ascending order, and the other one finds the smallest one by picking the first one. Clearly, we can combine the two algorithms sequentially to find the smallest number from a set of unsorted numbers. But to confidently connect both algorithms, we need to check their output and input specifications, and ensure that the output format is a set of numbers, and the property that these numbers are sorted in ascending order. Without a specification in detail, we will not be able to confidently connect both algorithms. Now, let's look at the third component, the procedure. We know that by definition, an algorithm corresponds to a set of well-defined steps that solves a problem. The set of well-defined steps is what we mean by the procedure here. The only thing that may be confusing is that while we have the common sense that some procedures produce random outputs, do these procedures qualify as algorithms? The short answer is that these procedures are algorithms, and the term well-defined does not conflict with randomness. For example, the step return a random number between 0 and 9 is a well-defined step that generates a random number. In fact, there is a class of algorithms called randomized algorithms, and we are going to discuss them later in this video series. Next, let's discuss the life cycle of an algorithm, which contains three main stages, namely the design, the analysis, and the documentation. To design an algorithm, we should first investigate the problem we are trying to solve. Investigating the problem allows us to know what conditions or assumptions are made by the problem, which translates into the input of the algorithm. And it will also tell us the mathematical objective of the problem, which translates into the output of the algorithm. By mathematical objective, we mean the property tied to the expected output of the algorithm. For example, we know that the output of a sorting algorithm is a set of numbers. The mathematical objective of the sorting algorithm is to ensure the following property of the output set of numbers. That is, for each number, it is smaller than or larger than the next number. Once we have investigated the problem and specified the inputs and outputs of an algorithm, we can think about designing the procedure. To be honest, designing the procedure is more like an art that involves a lot of human creativity, and it does not seem like a universal guideline exists for this purpose. Also, in many cases, it involves painstaking trial and error efforts. Fortunately, there are some algorithm design principles that we can begin with. For example, design principles such as greedy algorithms, divide and conquer algorithms, and dynamic programming algorithms have been applied to solve many important computational problems. Backtracking and branch and bound are also useful techniques to bring down the time needed by solving intractable problems. We will learn about these design principles later in this video series. Once we have designed the algorithm, we then need to analyze its correctness and efficiency. By correctness, we mean whether the output made by the algorithm can always achieve the mathematical objective set by the problem. For example, does a sorting algorithm always produce a set of sorted numbers? And does the shortest path algorithm always find the shortest path? If yes, we can declare that the algorithm is correct. After ensuring the algorithm is correct, we would like to know its efficiency in terms of both computation and space consumption. More precisely, we would like to study the asymptotic behavior of resource consumption by the algorithm and estimate its time and space complexity. If you are not familiar with these terms, don't worry, we will discuss them in more detail in Module 2. Finally, once we have ensured that the algorithm is correct and efficient, we have developed a good algorithm and will likely want to share it with other people. In this case, we will document the algorithm, which may involve publishing the algorithm in related conferences or journals. To document an algorithm, we need to specify all of its basic components. They are the input, output, and the procedure. We should also include detailed proof of correctness and the analysis of its time and space complexity. Documenting the design thought process is usually encouraged, as it may help people solve similar problems in the future. However, it is usually not required. Finally, I would like to clarify the relationship between algorithms and the problems they solve. First, one problem can be solved by many different algorithms. For example, we know that many sorting algorithms exist. On the other hand, one algorithm can solve only one problem. This is because the input, output, and procedure of the algorithm are all specified and well defined. Therefore, it cannot be used to solve a different problem. However, even one algorithm cannot solve many problems. It is possible to slightly modify an algorithm and make it solve a related or similar problem. For example, similar or closely related problems include the sorting and selection problems, the minimum spanning tree and the clustering problems, the maximum flow and the minimum cut problems, and so on. The mapping between different problems and how to solve one problem versus solving another problem belongs to the discussion of problem reduction. And we will discuss reduction in more detail later in this video series. At last, I would like to mention the difference between a problem and its instance. Usually, a problem is defined by its input and mathematical objective. Consider the sorting problem. Its input is a set of numbers to be sorted. Its mathematical objective is to ensure that, in the output list, each element is smaller or larger than the next one. On the other hand, an instance of a problem is instantiated with specific parameters of the inputs. For example, the input numbers 23, 5, 8 correspond to an instance of a sorting problem, and 15, 8, 9, 9 correspond to another instance of a sorting problem. Note that an algorithm should solve a problem, not an instance. In this case, when analyzing the correctness and efficiency of an algorithm, we should always consider all instances of the problem, especially the hard ones. It will give us more conservative assessment of the algorithm. In summary, in this video we have discussed the major components of algorithms, the life cycle of algorithms, and the relation between algorithms and the problems they solve. This is the last video of Module 0. In the next module, we'll begin introducing some sorting algorithms. Thank you for watching and see you next time.